Good morning, everyone. Let's start our lectures on Chapter 5, Quantum Price Level. Remember, in the last lecture, we talked about the overall basic theory of quantum finance, right? Using the enharmonic oscillator models instead of the path integrated model. As mentioned beforehand, basically there are two methods to implement or to formulate quantum finance. Okay, the first one is what we call the first generation of quantum finance using path integral method. Okay, basically by Professor because in Singapore. The basic problem is, although you can solve the problem, of course, but the basic problem is because you have to exhaust all the possible path from the start to the final condition in terms of time frame. So basically, you have to do a lot of calculation, okay, infinity in fact, okay, in order to explore all the possible path for the whole calculation. So technically, it cannot be done, especially when you want to implement real-time financial forecasts, predictions, or trading, that sort of thing. Okay, so especially when we want to implement that kind of system into our MT4 system for point tradings. So technically, it's impossible. Okay, although in theory it is okay. So that's why we have another method using the enharmonic oscillator model. So in the last lecture, we talked about the basic concept theory and also the basic formulation on how to come up with our Schrödinger equation on quantum finance, right? The QFSE. So today we continue the whole process. We work on the second part is how to base on this quantum finance Schrödinger equations without the time domain. Okay, what we call the time independent Schrödinger equation on quantum finance, and how to make use of it and implement it into our computer system. Okay, so in our terms is how to do the computational equations, okay, and how to implement these computational formulation equations onto computer system. That is the most important part. So later on in this course today, we will see we make use of what we call the numerical computational technique. Okay, it's a very important technique. In fact, as I mentioned in the book, okay, we base on this kind of computational technique to put all the weather forecasting equation into a computer system for calculations. So what we're doing is the twofold. First, we are using a new method to do the mathematical formulation, okay, using the enharmonic model. So the whole two methods are totally different, okay. And the second is what we will discuss today is how to make use of this formulation and implement this formulation into computer programs. So you can see in this lecture, we not only talk about how to formulate the whole system so that it can be converted into a computer program, but also we also show you the computer program as well. So we have two implementation methods, okay, in terms. Is the first one we are using MATLAB. Okay, all the time, as I always say in many of my courses, all the time when we try to do some implementations, in order to speed up the whole implementation process, we won't go directly into our C program or our Java program or our MT4 program. Okay, we will test the basic program, the core part, using some fast programming technique. Most of the time we are using MATLAB because MATLAB is easy for implementations, especially we have to work on some very big matrix. Okay, in our case, we work on the time series for the currency or for the forest, that sort of thing. So first of all, I will show you the MATLAB on how to make use of this new formulation onto the calculation of what we call the ener-gy level, the quantum price level. Okay, and the second part is how to implement that onto the MT4 system. So that part you will working on this in our coming lab. Okay, and Jim will show you the step on how to do that. Okay, part of the programming lab assignment. Okay, so which means after today's lecture, okay, you know the whole, what we call the whole big picture and solution on how to make use of quantum finance method. Okay, for us, we are using the enharmonic oscillator model. How to formulate so that it can be converted into a computer program. And secondly, how to write this program, okay, into two ways. First, simple MATLAB program, okay, very simple in fact, okay, and the whole step one by one to show you. Of course, you can do it by yourself using MATLAB. And second is how to implement the same program using MT4. The main reason why is we must do that, right? Because at the end, you have to integrate this quantum finance system, okay, into a MT4 program for real-time forecast and trading. So how to implement that into your MT4 program is very, very important. So we will work on that, okay? So let's start. So of course, as I mentioned, this lecture is corresponding to our book chapter 5. So as you can see in our previous and coming lectures, okay, I will specify the chapter so that if you have the book, okay, you go through the whole chapter, that's it. And basically my design for the book is something like this, just like my new book on AI. It's basically every chapter will correspond to 1 week lecture, except chapter 7. Because chapter 7 is on AI, and because I have to talk about the 3 most basic kind of AI method, the neural network, fuzzy logic, and genetic algorithm, it's quite impossible for me to discuss all of them in a single lecture. So in that particular chapter, I will fall into 2 lectures. But other than that, each chapter is a 1 week lecture, okay, just like today. So today is chapter 5 on the quantum price level calculation, on the basic theory, the formulations, and the programming method. Okay, so today is a bit, what should I say, is a bit technical in terms of mathematics and also in terms of computing. In fact, for the computing part is not so difficult. The difficult part, I think, is on the calculation part. But as I mentioned, all the step-by-step calculation already formulated inside the PowerPoint. So don't worry if you don't have the book. You just go through the whole PowerPoint slide. Okay, all the major content are already inside your PowerPoint. Okay, but of course, if you want to buy the book, even better, because the book will explain it more extensively, and also I have some chapter and exercise so that you can take a look. Okay. So today we will talk about what is quantum price level. In fact, we have already mentioned that in the past few lectures, but the difference is that today we will talk about the whole calculation technique. So you can see for my lecture all the time I'm using reinforcement learning, as I always say. It's all the time I will repeat some main point from time to time so that you have more ideas, so that it's more easy for you to learn. Okay, but of course I will add some new content. Okay, so today is on the calculation part. So today really exists, and how can we model it, and how can we make use of it? Okay, so today the most important part is not only on theory, is how to execute. Okay. So concept first. Okay, so what is the quantum price level? In fact, the quantum price level is become quite famous in Hong Kong and China because, as I mentioned, in the past 8 years, I have promoted in China, mainly in Shenzhen and also other major cities like Beijing and also in Shanghai. So in China, it's what we call the lens Java. Okay, it's using the quantum field theory or quantum mechanics to calculate all those price level. So for financial index, it will be the price index. For the forward currency or forward currency pair, it will be the index itself. For the current currency, of course, the price. Okay, so it depends. But all the time, of course, is the price or the price index. So as I mentioned in the technical analysis, in the old times, in the past 15 years, we are using different graphical method or using some calculation method. Most of the time it's very simple calculation to calculate the support and resistance level and also some index level. Okay, although at that time it's good. But as I mentioned, because nowadays we are all using computer and computer trading, it's rather impossible for you to convert all those graphical methods into a computer system, right? So of course we have to think about some more automatic way or more mechanical way to do the calculation inside the computers instead of a human graph drawing, this sort of thing. So that is the one reason we are using that kind of programming technique to do that kind of calculation. Okay, so in the basic theory, as I mentioned, the whole analog is the analog with an atom and the energy level with the market price level. So you can consider as the whole quantum mechanics world or the quantum world or the subatomic world, instead of talking about the atoms and the electron correlation, we are talking about in the financial world different currency or different commodities as financial particles. Okay, they will generate what we call the financial price field, and they are affected by itself, the field, okay, just like atoms, and by other neighboring financial particles. So it's what we see. We see the pounds, the US dollar, and the euro. Okay, so they exist in their own financial field and also affected by the others. So the whole logic is a kind of one-to-one correspondent, okay, and kind of a direct analog. So of course the most important part is how can we do the calculation. Okay, so in theory, everybody believe, especially in US, okay, that the main reason why is because of the more and more people believe in the basic theory on quantum mechanics and also quantum field theory. And also in the past 100 years, as I mentioned in the second lecture, is there are so many experiments that can prove the accuracy of the equation. Of course, we mentioned the Schrödinger equations. Okay, so that is the main reason why, the background reason. But of course, the most important part is if you want to make use of the analog, okay, on to finance. So of course, you have to do some kind of reinterpretation of the equation you're using, because the equation, of course, you have to make some changes so that it can be done in a computer system, okay, whatever kind of system you're using. Okay, so but the basic theory is quite makes sense because we talk about the electron in the atoms, okay, world, is that we have the what we call the ground state, the E0, and the excited state, right? So in terms of finance, they are all the same, right? Because after the closing, okay, of course, the whole market is closed and fixed the price. So you can assume it's a kind of a ground state. So once the market open in the next day, so for example, the daily is okay, it began to oscillate. So it's quite similar to what we observe in subatomic world for the particles. So in terms of quantum dynamics, okay, all these energy states are the what we call eigenenergies. So as I mentioned in the course on the linear algebra, as I always say, is all the time, basically, many dynamics, okay, can be described as a kind of eigenenergy and eigenfunction. Okay, that is the part of the nature. So that is why they are all related, as I always say. Okay, so the whole pattern are the same, but of course, the calculation are basically quite different. So as I mentioned, the equation is something like that, right? Okay, so you can see, as I mentioned beforehand, we are talking about the time-independent Schrödinger equations. Okay, it had two parts, right? The first part is the KE part. The second part is the PE part. And it is obviously is kind of eigenfunction because the function itself is the wave function in terms of the return R, right? and the E are the eigenvalue, they corresponding to the energy level. So which means it is a kind of a correlation function to correlate the wave function and also the discrete energy level. So it had embedded with some basic feature is the energy are quantized. It's in terms of mathematics, they are the eigenenergy function value, right? And in terms of quantum mechanics, they are the discrete energy level. So they are one-to-one correspondent. So for us, it's quite natural because we come across with this kind of eigenfunction for so many years. But of course, it's the first time, okay, in the past 100 years, we make use of it to formulate the relationship between the subatomic particles and also the corresponding energy level. Okay, so just like an energy in an atom without external force, this electron can remain in the ground state or some minute vibration. But more or less, okay, the vibration is just type related to the ground state. So remember, as I mentioned before, the R, okay, is the price return, right? But this price return is a relative means instead of it is the R corresponding to the central state. Okay, so it's quite makes sense. So similarly, without then any external effect or stimulus. So, for example, some financial events, just like now we have the coronavirus, and some breaking news, some index figures released, just like the interest rate in US, and also the MPI, one of the most important index, okay, in financial. So without these external stimulus, all these financial particles are vibrating, okay, just like a random kind of oscillation, okay, corresponding to the ground state, okay, until they have some external stimulus, and it will jump from one energy level to another one. And that sort of thing are controlled by these beautiful Schrödinger equations, okay, that related, okay, the price return together with the energy level in terms of very beautiful eigenfunction, okay. So, however, when this is a significant stimulus, neither directions, okay. So, this financial particle will jump from one energy level to another one. So, as I mentioned in technical analysis course in the past few weeks, is in the old days we have support and resistance level. All the time they are not the same level. But nowadays, because we are using the quantum energy level, so we don't, okay, differentiate which level is a support or resistance. We just call it energy level. So in terms of point trading, it's even more makes sense because for point trading, the point just write their own trading programs and consider some intrinsic level, okay, for the price for trading. Because all the time you can imagine when you do write a trading system, of course you have some guideline to do trading or not, right? So these, of course, this threshold in some sense you can see as a kind of a decision-making level. So in terms of programming technique, okay, we don't differentiate which one is support or which one is resistance. It's just the price level. So that part is quite consistent and also related to our understanding on the energy level because they are just energy level, which means these are the fixed level that the price can be, okay, stay with, okay, for both directions, of course. So after that, the market maker will absorb the stimulus and the financial particle will come back to the equilibrium state. So what I'm saying is, remember in the last lecture we talked about different partners, okay, and participate in a financial market. Okay, the most important part, of course, is the market maker. The market maker provides the market, and also every time there are people buying and selling, okay, and every single second they will try to exchange the order, right? And the market maker is to, okay, what we call not to control, but to maintain, okay, the market movement, and also try to absorb the stimulus all the times, so that all the time it can be synchronized with different market. So in terms of the quantum particle theory, of course, it's the same case. Every time when they try to move from one to another, so one to one level to another one. So at a particular moment, it tries to regulate the whole market so that it can be stabilized in that particular energy level until there's another stimulus occur. Okay. So does such a quantum price level really exist? Okay, of course we don't know. But as I mentioned beforehand, that analog is very, very similar to what we consider in terms of S and R. The only differences is we don't specify is S or R, because all the time, as you can see in this chart, okay, a support in one particular time frame can be a resistance in another time frame. Which means in terms of trading nowadays, our belief is S and R are just the price level. That can give you some guidelines for where the price can stop. Okay, either in this direction or other direction. But before that, it will stay in that particular direction for a moment. Okay, and wait for the next stimulus in either directions. So in fact, in terms of the technical analysis in the past 15 years, okay, we have that kind of concept. And of course, nowadays, because we have now so many problem trading systems, and especially for the high frequency problem trading, okay, so that kind of concept become more and more strong, because once you have that kind of level, if you can calculate, it's more easy for you to write the program to do the trading. Otherwise, it's very difficult, right? Okay, so once we believe, that kind of thing exists, and can be formulated. So the next part is how to do the formulation, the model. Okay, again, we come back to the beautiful Schrödinger equation from what we have learned. So first, we have the time-dependent Schrödinger equation, which we have the wave function, the Hamiltonians, and also the time frame. So of course, we also have the time-independent one. The time-independent one you can consider as another angles to take a look on the quantum world is we forget the time. We just want to see the big picture. So the whole analog is the differences between you take a look on the energy level or on the detailed Newton dynamics. So if you only want to know, the energy level and different height from the ground, so we will talk about that kind of thing. Because when you talk about the potential energy in terms of classical physics, so that kind of thing is time independent, right? It's time independent. When will be time independent? When you take a look on the detailed dynamic from a particle moving from one position to another position. Of course, according to the Newton law of motion, we have that kind of formulation. And that formulation, of course, related to time. But when you talk about the potential energy, the potential, the weight, that sort of thing, they are time independent. So you can see time-dependent Schrödinger equation and time-independent Schrödinger equation is all depends on the way you look into the problem. The world are always the same. But if you take a look on the problem in different angle, of course they are different. So there's two different ways to take a look on that, of course. So in terms of the time-independent Schrödinger equation, not because it's simple, but because you take a look on the total whole picture. We take a look on the wave function, independent of time, and also the possible energy level it can exist. So which means the whole problem are still the same, but you are using a particular angle or perspective to observe the whole world and extract the information you want. So which means in this case, we are only interested in the energy level it can exist. So it's not a correct or wrong, that kind of thing. It's the different angle you see the problem. So our focus is on the energy levels. But of course, because of this, the whole equation become more, what should I say, is more easy to solve. So you can see the difference between our method and the path integral method is path integral method, of course, all related to time, because it have to exhaustive to calculate every single possibility from one time to another time. So of course, they are all time independent. So when it is time independent, as I always say, it becomes very complex because there will be many different kind of possibility, right? So the whole calculation become a bit more easy. It consists of the Hamiltonian two parts. First is the KE part, okay, and the second is the potential part. So we have two. So again, remember in the quantum finite Schrödinger equation, we are using R. R is the price return. Okay. So say for example, you are using a particular currency pair, USD and CAD, US and also Canada as an example, because it's also the one of the majors current force pair. Okay, overall with the largest amount of transaction every single minute days. So we can write the whole equation like this, okay, as we have already mentioned this. And well, the Hamiltonian have the KE and the PE part. The first is the KE part, the second is the PE part, okay. So we have already talked about that. In terms of finance, we have some analog. The analog is the Planck constant, okay. Under many theory, okay, we believe that, okay, it can be represent the uncertainty for the market behavior. And of course, for the mass, the one-to-one corresponding is it should be related to the financial market capital, right? So these are what we call the mass, okay, for the market. Of course, it's capital. So if you analog, the mass for body is a mass. The mass for the financial market, of course, is the capital amount, right? So it's the capital. Which means the biggest the market, so for example, Dow Jones, the biggest the M, okay, the mass. So in quantum mechanics and quantum field theory, the wave function have a very special meaning. Of course, it is the big picture, right, of the market behavior as a kind of wave. Okay, as the dual analog, right? When you take a look at a particular particle, the wave disappear. It will become the particle motion. So that's why we have two calculation methods. So what is the wave function in quantum finance? Okay, so can we observe that? And also, can you measure it? Or can we calculate it? Of course we can. So remember the double slit experiment, the beautiful one with the two slit for the photon or electron. Okay, we have two ways to visualize this, right? Without any one-to-one observation, it will become a pattern, just like a wave. Okay, and that wave pattern, of course, is a kind of a statistical distribution when you take a look at the end, right? So we can make use of this. And in fact, this kind of wave pattern, of course, is a kind of historical statistical figures when you collect the time series figures, right? So it's a one-to-one correspondence. So in other words, if the financial particle really have the duality effect as a quantum world particles, so technically speaking, we cannot measure the discrete quantum energy level, okay? But we can observe just the wave function as our overall big picture, right? So what should we do? So remember in quantum mechanics, we measure the probability density function, the very beautiful function, right? So using this one, okay, you take the and in the quantum finance, the wave function can be observed using similar manner. So remember, for every single financial elements, we have over 2,000 trading day pattern. If you talk about the daily fluctuations, so of course these 2,000 trading days return, okay, -1, will be the overall probability density function distribution, the whole statistic. Okay, and you can put it into a kind of a histogram. The x-axis will be the return, so the central must be 1. Okay, no change by day. And the right-hand side is the one that the next day is higher than the previous day, and the left-hand side is the next day is lower than the previous day. So which means the right-hand side is the positive R, the left-hand side is the negative R. Okay, so for every single financial product, we can base on this 2,000 trading days return, okay, and put it into our histogram. Okay. So we can do that. So the next day will be the histogram we report. So something like this. Very beautiful. So you can see for every single financial particle, it should be something like this. The more data you have, the more beautiful or the more smooth, okay, the particle distribution is. And more or less, I can tell you, more or less is a normal distribution. And the standard point, more or less, okay, not exactly more or less, is equal to 1. Equal to 1. Unless there is a very special case. The whole markets are being biased by some special system. But you can imagine if you talk about 2,000 trading days, which means about more than 5 years. So all these local slice effects should be waived out. So the whole distribution will be just like what you have collected in your double slit experiment. You get the whole big picture, okay, for that particular financial particle. That can be represented, the whole PDF, for that particular quantum central equation for that particular financial product. Okay, so this graph is what I put in the early 2019 when I write the book. Okay, at the beginning of the years, and also these are the 5-year statistics. Okay, and put it into a histogram for the distribution of the XAU is the goal. Okay, in terms of USD. So the whole calculation is very simple, right? The number of currents is the event R and the total number of event E. So you just put the statistic, okay, for the price return. Okay, remember the price return daily. So, and there are several features. First, the wave function are more or less fall into a standard normal distribution. Okay, you can try and you will see. The second, the maximum, also the mean of the occurrence is very close to 1, but not exactly, but very close. Okay. So basically, the wave function is symmetric with the central axis. So it's very normal, right? Because it's quite a normal distribution. It can be reflected by the fact that the whole financial equation is symmetric with respect to the ground state. That's true. As you see, the equation itself is very beautiful in some sense, so it should be symmetric. Of course, it's not 100%, but very similar. Okay. In other words, we can evaluate the excited quantum finance energy level E1, E2, E3, which corresponding to the positive quantum price level, or the negative quantum price level will be deducted automatically because they are symmetric, right? So you will see that version. So quantum price level, solving the quantum finance Schrödinger equation. Quantum finance Schrödinger equation is given by the guy, okay, very beautiful one. With remember the kind of order. So you can see it's the relationship between the wave equation in terms of the price return R and also the energy level. And you can see for the potential part, for the what should I say? For the KE part is very standard, okay, Hamiltonian part on the KE part. For the potential part, you can see it consists of 2 factors. One is the order 2 in R, one is the order 4 in R, okay? And these are all the parameters, remember that, okay? So when we have the method to calculate the wave function, which means the PDF. So which means when you take a look on the wave distribution, in fact, these are the wave function, okay, you see, okay, in terms of time independent rate, because you collect the whole statistic, so they are of course time independent. So you can consider it as 2-part, okay. So when we have the method to evaluate the R, okay, so as you see, the central equation is how to find all the energy level, right? Which means how to solve this certain equation in order 2 and order 4. There are many methods in so many years, okay. Until that we have a very simple solution. Until we have a new kind of calculation, you will see. So we come to how to solve the equations, okay, that part. So numerical computation. So not until 2007, okay, Jasper and the team write a very important paper on the what they call simple static ener-gy eigenvalue of a quantum and harmonic oscillator. So in this paper, they spent so many years to solve a kind of what we call lambda x 2m quantum and harmonic oscillator equations. They were funny, okay, for many years until they got a very, very powerful and simple solution. So after that, we based on this, we can solve the problem automatically by computers. So that is the turning point. Okay, before this, okay, this equation is very difficult to solve. Okay, but after that, it have a very, very simple solution. So we base on this to continue our calculation process. So how to do that? So first of all, you have to learn what is the lambda x2m quantum and harmonic oscillator model. Okay, they call this the AHO. It's something like this. So you can see, it is a standard Schrödinger equations. Okay, time independent. So it's E and also the wave function tri. And also it have the Hamiltonian part. Okay, Hamiltonian part of two part. First is the KE part. Okay, same as ours. The second is the PE part. PE part have two terms. You see, for the x, it have the second order term, and also for the lambda x2m term, which means it can solve a particular group of Schrödinger equation that have a second order combined with order to the 2m, which means it can solve the x2 and x2 times any integer, which can be x4, x6, and so on. Okay, so you can see what I'm saying, because we are powerful. So it falls into this category when we set m to 2, right? That's so good. So in which the excited energy level can be solved approximately by the following polynomial. That's all. So once you have this pattern, your Schrödinger equation, it can be solved by solving this equation, which means you can turn your whole calculation into that one. That is the good part. Okay, and by doing that, we have the chance, okay, to calculate the lambda. Okay, so let's continue. So once we do that, so if we take a close look of the quantum financial equation we have, okay, in fact, it's what we call the quadratic harmonics and harmonic oscillator, which means the x second part is the power form, okay, which means 2m when m equal to 2. So we have converted the quantum financial equation into a lambda x2m once we have this. So we set m into 2, right? So it will be that part. So which means the whole problem can be fall into that category, and it can be solved by the solution part they have. So which means if we normalize the quadratic terms R2, so you just put in the other one, okay, with the quadratic terms of R4 and combine into coefficient lambda. So look that lambda is different from the previous one, okay, but in order to make it simple to understand, I put it into lambda, but although they are different. So besides, the KE part is also normalized with the coefficient set to 1. Why? Because in usual practice, as seen in many papers, in numerical derivation of the quantum Schrödinger equation, as one might find out that we can discuss the KE part during the course of variation for different energy level. The main reason why is all the time we assume the market maker will try to absorb the whole market, so the KE part will try to what we call stabilize into the new excited or new lower state. Okay, so that's what I mean. So once we have the quantum financial equation in the forms of 5.13, we can make use of the numerical solution of the quantum energy level in 5.11 by setting m equal to 2. So we have something like this. Okay, so as you can compare with the previous one. I mean this one. Okay, set m equal to 2. So the whole world becomes very simple. Yeah, it will return it 2. Or what we call it, they are the same, right? So where the k, okay, by the paper is this one, okay. Although it seems to be very complicated, but if you put in the computer, it all becomes very simple. And n, of course, is the energy level, okay. Notice that the numerical equation 5.14 and 15 can easily be calculated by MATLAB. The main reason why is that MATLAB has a very powerful function called root, okay, that can solve this cubic equation simply by itself. Okay, we will make use of this. Okay, but luckily for MT4 and MT5 we don't have that particular function, so we are using another method. So which means in this lecture we will talk about two methods. Okay, method number one using MATLAB because we have simple tools to solve the cubic equation. So it's easy for us to calculate lambda because it's a very typical cubic equation, right? And for the MT4 and 5, okay, you are using some other method. Okay, I will talk about this later. So in summary, once we know the coefficient lambda, okay, the whole quantum energy level can be solved one by one. Okay, you can see. Once you know the lambda, all the things can be solved. Right? So how can we find lambda? So we will come back to the pattern again. So remember, in order to find lambda, we have to reset the quantum finance energy Schrödinger equation, this one. So as mentioned, this equation has four major characteristics. First, it is a very typical enharmonic oscillator with two terms. First is the harmonic term, okay, the first one. The second one is the enharmonic term, the second. We also call it the propagation term. So it consists of two parts, the KE part and also the second part, the PE part. So the quantum finance wave function defined R, okay, if we measure it with sufficient samples, say for example 2,000 training days, it will be a very beautiful normal distribution with the maximum very close to the mean, as I mentioned, okay, and you can observe if you plot the histogram, which is also a stable ground state with K equal to 0, of course. So the quantum finance wave function is symmetric, okay, the same part, in ground state SS when the sample is sufficiently large. So we make use of this. So we are using method what we call the finite differences method, FDM. Okay, so it's simple. With the advance of computer technologies, FDM, the finite differences method, what we call finite difference, provide a very simple way to solve the differential or higher higher order equation by numerical approximation. So by using the original position by Newton, right? It cut into pieces. Remember that in terms of calculus, the whole theory of differentiation is that you cut into pieces and you calculate the slope, right? And for the integration, you cut into pieces and add them up. So in terms of computer, of course, you can do so. If you have sufficient data, okay, and samples, of course, you can cut into small pieces. And then you calculate either the slope or the area. It depends on what you want to do, right? If you want to do the differentiation, okay, the slope. If you want to do the integration, the areas. So it depends. So we call this method finite differences. So although such techniques are using in numerical approximation, okay, but if you have sufficient large amount of data, it is very accurate in some sense. Okay, so the calculation is something like this. So we have two full process. So for a function, qx, we divide it into small pieces. And then set the value as xi, as yi. And then the finite differences formulation will be something like this. The dx, of course, will be these small pieces, right? The first order differentiation will become the slope, right? yi plus 1 minus yi over the pieces width. And the second order, again, will be this one. So you can see the first and second order become very simple. Okay, and I can tell you that it's very accurate if you have sufficient data to do the chopping. So that's all thing. So we call this finite differences. So once we have this, okay, we can do the same things, right? Onto this. As you can see, I just using the same plot, but this time I cut into small pieces, right? So it's still the normal distribution. It's still the normal distribution. So this figure shows how can I convert the what I should say, the wave function into different slide, and then we try to do the finite differences and to evaluate, okay, the lambda. So so the first of all is how can you define the So it is the technique. Okay, for me, I'm using the phi times the for all the distribution. Of course, you can calculate the mean and also the standard deviation, right? After many testing, I'm using the del x as the phi times of the standard deviation over 15. Okay, so because I want to cut it into 100 pieces, each part has 15 pieces. Okay, so of course you can use some others. Okay, it depends. Okay. So these figures also show the regression curve for the wave function for illustration purpose. So you can see the regression curve just for illustration. Okay, no specific. And also the actual distribution in terms of different slide of the delta x. So you can see for each part I have 15 slide. Okay, so totally we have 100. But I can tell you that when you do that calculation, you have to do some trial and error because the size, okay, of your slide, you will affect, of course, the calculation. So you have to choose. Okay, so it depends on how many observations you have, of course. Okay, so of course, for the phi maximum, of course, is close to 1, the ground state, what I call. So the ground state have two parts, the positive part and the negative part. Okay, one the right hand side, one is the left hand side. As I mentioned, they are symmetric in some sense. Yeah, that's true. So they're symmetric, and also based on the slope, you can calculate, okay, their first order and second order derivative. So finite differences method. Yeah, we're using this one. So for the central part, it is the higher part. So you know at that part the KE is close to 0, and the left and right should be very symmetric, and that particular moment. Okay, not the others. Because for the others, not the case, right? So for that one, to represent this dynamics. So in this figure, we show three major R segments. The central part, the RO, the -1, the left hand side, and also the right hand side. Okay, the R plus 1. So it corresponded to the ground state, and the first right hand side and left hand side R state. Okay, two particular directions. So as mentioned, according to the Schrödinger equation, they are symmetric in some sense at the central part, only at that part, and the KE is equal to 0. Since we have all these 2,000 Ks of oscillation and the R, of course, we can calculate the slope. So to evaluate lambda using finite differences, we have two options. Option number 1, using the finite differences method to evaluate the boundary case of RO and R plus 1. Okay, which means the rightmost approximation of RO and the rightmost approximation of R1. Okay, leftmost approximation of R1, that's 2. Or you can using the finite differences method and the symmetric property. For me, of course, this one. Because this one is more safe in some sense, you can imagine. If you have sufficient data. Okay. But of course, you can try the first one if you want. So we use the gold against US dollar as an example. Okay. So by using this, okay, I'll just throw it out first. Yeah. By using this, I'm using 2,000 Ks. And then after calculation, we have the number of sample, 2,046, because we have the boundary case, you have to K out, right? And the maximum, okay, is Q, is the 2 and 204, okay, out of 1 as the maximum, of course. Okay. The RO is very close to 1. So the first one is 100,396. It depends on your slide, of course. And the other side is something like this. And we calculate the Q value at this 3 point. So once we have all this, of course, we can calculate all those remainder value, right? So fall into this equation. Since the quantum finance equation is matched with the 2 part, okay, so we can have that kind of equation, right? Because the KE part cancel out, so we can equalize these two. And then we can calculate the lambda by doing that. So you can see all this can be found, right? The phi R1, R plus 1, and R minus 1 we have. The R itself in 2 parts also have. Okay, and the second order and fourth order, you just do the calculation. So all this we can find. So by doing this, we can calculate the lambda is 1.168, okay, and 13758. So of course it is the golden ratio, right? And the next figure should be the lambda value of all the 124S product using the MQL program. Okay, so you can do that. Okay, if in your lab, okay, by using the empty form. Okay, you can see. Okay, so the first one, the silver is silver is 1.198. Okay, and also the others, okay, as well. So all of them are differences. You can see. Okay, there is no pattern at all because they are different, of course, right? But you must have can calculate the rate, of course. So once we have the lambda, we can use this equation to evaluate all the energy level. So we calculate the lambda first. Okay. So once you have do this, okay, you put it into here, and also the k is something like this. So that the equation in file 5.14 is a typical cubic polynomial, order 3. Right, order 3, the order 1, okay, and order 0. Yeah, we don't have the order 2. Yes. And in MATLAB, no matter what, it's easy to calculate because MATLAB have a function called root. That's good. So we can calculate that. So the MATLAB version, okay, and in fact, I don't go through in detail because the calculation part is not too difficult. The only thing is it has the root function for you to solve this cubic equation. Yeah. Okay. Of course, you can do that. Okay. In fact, you have to do that in the lab, as far as I remember. Okay. For the MATLAB part, it's not difficult. Just put it into the MATLAB and solve the equation because it has the root to calculate all the root for the as you can see. Once you solve the equation, you generate experience. All those solutions, they have the real part and also two complex solutions. And these two complex solutions is symmetric. Of course, we get the real part. The real part is the energy level we are talking about. Okay. So how about for the MP4? Because MP4 don't have the roots, so we are using another trick. Okay. This trick is not difficult. If your mathematics is good, okay, already you have the solution. Because there is one guy called Cardio, okay, and Cardio is born in the 1843. The reason why I know because he's a close friend of Leonardo da Vinci, okay. He is also an Italian mathematician, okay, chemist, physicist, and so on, okay, and gambler, of course. And it had discovered one important thing, what we call how to solve a cubic, depressed cubic equation. Depressed cubic equation is the kind of cubic equation without the quadratic term, the square term. So, which means it's fit to our case because our equation is the cubic equation without the quadratic term. So, which means that kind of thing. So you have the ax3 plus bx plus c equal to 0. That's all thing. So if you check with the website, okay, Google or Wiki, you can see the whole calculation. The whole calculation is to solve that kind of equation. So the solution set is something like this. Okay, I don't go through in detail because these are all well known. And the most important part is the solution set itself. Okay, by solving these equations, we can find these two solutions, cubic equation. Which means, in other words, is you just need to put these two solutions into your empty form. Okay, all the problems solved. Okay, because it tells you how to do the calculation. Okay, which means there is in other words, there is a shortcut for you to solve this depressed cubic equation without detailed mathematical analysis. Okay, it tells you the whole solution. Of course, you can see for this equation again because it's a cubic root, so that it will have 3 solutions, 2 complex number and 1 real number. Of course, we only need the real number at the solution. So you can check if you are reading the lab, you can check this against the MATLAB solution. They are the same. Okay, of course there are some detailed differences in the maybe in the 10 figures or so. I don't know, but overall they are the same. Okay, so that part is important because you have to do the implementation. Okay, so at time of cardio there is no concept of complex number. That is the funny thing, but of course, as you can see from that, the T have because it's a cubic root, so that it have two pair of a symmetric complex root. And in our case, we only need the real root. So for our case, it's much more simple. Okay. So the MQL version. So once we do that, in fact, we are using the same thing. We put it back into our cubic equation. Okay. And then we can calculate all the En. So the En is just this one, which means in your implementation, you only need to put it into your calculation. And we replace it one by one, of course. Red P is this one, and K is this one. That's all thing, right? So not difficult, but of course when you do the calculation, better you compare with your your MATLAB equation. So for me, I'm doing this. First, I implement the MATLAB formulation first, and then I using the MQL, and then I compare the result, and then I can make sure the calculation is correct. In fact, the calculation is not difficult. That is the main part. You can try this in your lab. Highly recommend, of course. In fact, it's part of your program assignment, I think, right? So, of course, we can try this in a complete version. So once you do that, okay, which means you can write a whole algorithm to compute all the energy level for every single product. Okay, so first, with the data series, calculate the price return, okay, and plot the graph, which means calculate the wave function, okay, and calculate all the parameter, right? The sigma, which means the mean and standard deviations, and also the Q value, okay, and do the normalization. And so once the L is found, using the quantum financial equations to calculate so all the lambda values, okay, and also calculate the price return based on this. So once you have this, okay, you can your price return is something like this, right? The one you this one, and then you calculate the normalized QPL. After that, you normalize it, okay, you mean the normalization method, and then you save two level of data file. So for each financial product, save the QPL table. Contains the content price return, the content price energy level, and also the normalized one, okay? And then for all financial products, create the QPL summary to calculate all different energy level one by one, right? So not difficult, but remember to do the proper normalization, okay? So for the QPL, for the just using one, for example, right? So we have this one. So we have all the energy level you want. Okay. Remember, because in our theory, the two parts are symmetric. So the positive part, you are using this one, right? The negative part, we can use this one. One is time, one is the opposite one. Okay? So you can have two parts. Right? So once you have this, we can calculate every day the quantum price level, one by one, like this. So up to this, okay, we talk about different things. First, we talk about the whole quantum finance theory. We talk about how to convert it into enharmonic oscillator equations, right? And how to calculate every single energy level by using numerical method. More importantly is how to put it into not only in MATLAB but also in MT4. So that, which means we can automatically calculate every energy level and price level in real time for every single product, so that we can use it for first for the quantum finance forecast. We'll talk about this later on. And also second is how to do the trading. So we'll talk about this one by one. So the part on how to make use of quantum finance to do the quantum finance price level complete. So the next part is how to make use of this level to do the trading and also to do the forecast. Okay, so we will continue in the coming lecture. Okay, so in the next lecture, we talk about the quantum trading and hedging strategy in the next week. Very interesting. Okay, and let's see next week.